Hello everyone, welcome to the week 6 and module 6 of this microsensors and nanosensors, in which we are going to discuss about temperature sensors. This is the first lecture in this week. So what is a temperature sensor? We all know that a temperature sensor is a device that measures a degree of coldness or hotness of an object or a surrounding. Okay, so if I have a device, it can also monitor temperature. When I say temperature, it means the degree of hotness and coolness of an object or the environment around us. Okay, it basically convert temperature measurement to some electrical signal. Because we are discussing this under microsensors and nanosensor of electrical engineering course, we are mostly discussing all these sensors in the context of electrical signals. Okay, so a temperature sensor, basically what we are going to discuss in this course are the devices which convert the measurement of this degree of coldness or hotness to some electrical signal. The electrical signal we have already discussed in the first module, that are in the form of change in voltage or change in current or even change in the charge. So the application of this temperature sensors are tremendous. Okay, the four major applications of this temperature sensors are in the industry process control. Similarly, we have seen other physical sensor, which was humidity sensor, which was part of our week 5. That is also a crucial sensing element in the industrial process control. Okay, so it covers the monitoring and controlling temperatures in the manufacturing industry as well as other industry. We know that you talk about a steel industry or a simple blast furnace, the temperature has to be monitored from say minus some 200 degrees Celsius to 2000 or 3000 degrees Celsius. And when I say these degrees, it has to be precisely monitored. When I say 2000 degrees, it has to be precisely around 2000. I mean, plus minus 5, 10, 20 degrees Celsius is fine, but you cannot expect that 2000 degrees Celsius plus minus 200 degrees Celsius. Okay, so this has to be monitored, then only this industrial process sustains. Okay, then second major application of these temperature sensors are in the consumer electronics. Okay, be it regulating temperature in appliances, for example, our household appliances including the refrigerator, washing machine, the geyser, heaters, all includes the basic temperature sensors. Okay, our air conditioners are biggest example of this the temperature sensors. Okay, so if you want to set the temperature for a pleasant stay, you usually set at 20 to 24 degrees Celsius, so that your air conditioner is actually monitoring. At the same time, it is of course cooling the room. Okay, so it has to be monitored. So if it is, you set it to 24 degrees Celsius, but it is say it monitor erroneously and it reads say 30 degrees Celsius as 24 degrees Celsius, you may feel uncomfortable. Okay, so in consumer electronics, these temperature sensors has the biggest application. The third application of this temperature sensor is in the automotive industry. Okay, so be it monitoring cabin temperature of your car, monitoring the engine temperature or other critical parts of your vehicle. Okay, all these things are done by temperature sensor. Okay. Then of course environmental monitoring is the major application of these temperature sensors, be it tracking temperature in your room or be in your office. Okay, to applications such as in smart buildings and smart say factory or smart hospitals. Okay, these are the major application apart from measuring temperature of the soil and water. Okay, so I mean, what I want to say is the application of these temperature sensors are tremendous. You will find that these temperature sensors are nowadays essentially part of all the electronic systems that you see around you. Okay, be it your television, be it your mobile phone, be it your computers, everywhere you have this temperature sensor. Okay, so we have to understand these temperature sensors in a little detail. Okay, the basic principle behind most of the temperature sensors is based on modulation of some of its physical property. Okay, of course with respect to temperature. We have already seen for other applications like gas sensors, chemical sensors or humidity sensors. Those sensors were also based on similar phenomena where some of the property of a device is changing with respect to the analyte or the stimuli that I want to measure. Okay, similarly this kind of devices changes some of its physical property with respect to applied temperature or surrounding temperature. Okay, let's see some example. Say one example is RTD. We'll discuss about RTD in more detail. In RTDs, the electrical resistance of the sensing element changes with the temperature. Okay, similarly for thermistors also, the resistance of the sensing element changes, but it is more significant in case of thermistor. In this course we'll see what is the difference between RTDs and thermistor, although both are based on the change in the resistance with respect to temperature. Okay, then there is another kind of device which are known as thermocouples, in which a voltage difference is generated between two dissimilar metals when they are at different temperature. Okay, so similarly IC temperature sensors, where you have mostly semiconductor devices in place and there is a change in the voltage with respect to the temperature applied. Okay, so the sensors that we have just discussed can be divided into two categories. One is contact sensors and another is non-contact sensors. Okay, these RTDs, thermistors and thermocouple all are basically categorized under contact sensors. So whenever it comes into contact of the object, then only it can tell you about the temperature, while there are some non-contact sensors also, which is very interesting. For example, infrared sensors. Okay, in this COVID-19 scenario, you might have seen people checking the temperature of or the fever level of a person by using a gun kind of structure. Okay, so they were basically the infrared temperature sensors. Okay, so in this course we are going to discuss some of these sensors in little detail. Okay, let us learn first thermoresistive sensors, because we have seen that RTDs and thermistors are majorly dependent on the tunability of the resistance with respect to the temperature. Okay, so the electrical resistance of various materials depend on temperature. We'll see the equation that how the resistance of a metal or a semiconductor also for some cases changes with temperature. However, the advantage of this sensitive resistive sensors are they are very simple. Okay, what you are doing is you are giving some temperature and its resistance is changing. Therefore, the interface circuit designed for these sensors are very simple. They have good sensitivity or decent sensitivity, I would say, in the desired temperature range. Okay, so if your operation require say -100 degrees Celsius to +100 degrees Celsius, you may get a desired RTD for your intended application. Okay, and another good thing about these sensors is they have long-term stability. Okay, so you can use it for longer time, maybe for years. That's why it has found its application in industry. Okay, as I have mentioned that these sensors can be divided into various groups. Particularly these thermoresistive sensors can be divided into three different groups. First is resistance temperature detectors, which are RTDs that we are discussing. Okay, then we have thermistors and then PN junction detectors. All are dependent on modulating the resistance of beats a metal wire or a semiconductor film or a simple PN junction. All these things, all the resistance of these things changes with respect to the temperature, and if we can detect it, we can say that this device is acting as a thermoresistive sensor. Okay, please note that these thermoresistive sensors is categorized as absolute temperature sensor. Okay, because they can measure temperature that are referenced to an absolute temperature scale. Okay, we have discussed this absolute sensors and relative sensors in our first module. Okay, for most of the metals, the variation of resistor R with temperature T can be represented mathematically as RT is equal to R naught into 1 plus alpha 1t plus alpha 2t square, alpha 3t cube, and so on, alpha n e to the power N, where this R naught is the resistance at temperature T equal to 0, and all these alphas are constants. Okay, this RTD that we are going to discuss is basically used for metal sensors which are fabricated as wires as well as thin films. Okay, this RTD include certain semiconducting materials also, like germanium. Of course, the semiconductor has to show strong temperature sensitivity, then only we can categorize it under RTDs. Okay, the temperature dependence of the resistivity of all metals and most of the metallic alloy make them suitable for use in the temperature sensing application. So for more, you will see that most of the RTDs are either metals or their alloys. Okay, although nearly all metals can be used for this application, platinum is preferred over all others. Okay, because of its predictable response, long-term stability, and durability. When I say predictable response, means extrapolation of the curve for this platinum temperature dependent graph is possible. Okay, tungsten RTDs are usually applicable for temperature anything over 600 degrees Celsius. So typically this platinum RTDs are applicable for minus 200 degrees Celsius to around 630 degrees Celsius or so, although it can be, in a special case, it can be used till 850 degrees Celsius, but mostly for above 600 degrees Celsius, tungsten RTDs are used. Okay, please note that all RTDs have positive temperature coefficient. Okay, and I think this is the major figure of merit, or you say major characteristic of a RTD. Okay, and it separates it from thermistor. We'll see that in detail. Okay, please note that RTDs have positive temperature coefficient always. Okay, consider thin film RTD of a platinum. Okay, again, since we are talking about microsensors and nanosensors, these thin film RTDs are very popular for this microsensors application. Okay, and usually this is fabricated by patterning a thin film of platinum or its alloy and depositing on a substrate, usually ceramic substrates, basically Al2O3 sapphire substrate or some other kind of substrate. Okay, so this is kind of platinum thin film layer which is patterned. If you see, kind of serpentine kind of pattern has been given to this film. This kind of pattern is always possible by using say shadow mask or even by patterning using lithography. Please note that these structures are microstructures mostly, so that's why I have mentioned that even without using a lift-off process, it can be patterned. Okay, the RTDs are often made in this serpentine shape to ensure sufficiently large length to width ratio. So in a small space, you can generate larger area of this thin film. So the aspect ratio of this sensor, particularly the patterning of this platinum, is high. Okay, now for larger structures, wire wound RTDs are also popular. Here the platinum winding is partially supported by a high temperature glass adhesive inside a ceramic tube. So you see, this is your platinum wire and this is the ceramic bobbin on which this has been wrapped up. Okay, and similar to the previous one, the thin film one, where you have this two leads, the two leads is also popping out of this bobbin structure. Okay, this construction provides a detector with most stability for industrial and scientific applications. Okay, so what are the requirement of a metal to be eligible for RTDs? So the requirement of a conducting material to be used in RTDs are the change in resistance per unit change in temperature should be larger. Okay, so if there is a small change in temperature, the change in resistance should be even larger for that. Okay, the resistivity should be of course higher. The resistance should have continuous and stable relationship with the temperature. Okay, and it will ensure the large dynamic range for this RTDs. Okay, Say, I will give you some example of some metals which are actually not used in RTD applications, and the most popular example is gold and silver. Okay, so gold and silver are rarely used because of their low resistivity. So out of the three qualifications, characteristic that I have mentioned for conductor to be suitable for RTD applications, where the change in resistance per unit change in temperature should be larger, higher resistivity, and the resistance should have a continuous and stable relationship with temperature. But gold and silver doesn't qualify for this because of their lower resistivities. Okay, although the tungsten have relatively a higher resistivity, but it is reserved usually for high temperature application, as it is extremely brittle and difficult to work for this intended application. Okay, copper is also used occasionally for RTD element, as it has low resistivity, but its low linearity and low cost make its economical alternative. So usually, if even the platinum alloys is costing you more, copper usually replace that. Okay, but this is very rare nowadays. You will find mostly platinum based RTDs. Okay, the industrial platinum resistance thermometer looks something like this. You can see that you have the basic element, sheath, the lead support, mounting threads, and the connecting thread, and this structure is very popular for the industry platinum resistance thermometer. This is your the temperature monitoring element. Okay, the platinum part basically. Okay, so the RTDs are this industrial platinum resistance thermometer, although its name is platinum resistance thermometer, are usually made up of platinum or its alloy, but nickel and nickel alloys are also used for low cost devices. But of course it will have a limited temperature range. Okay, and they are quite non-linear, and of course they tend to drift over the time. Okay, so for measurement integrity, of course platinum is the major choice. Okay, the resistance versus temperature curve are shown for a few materials under resistance thermometers. Just have a look on this curve for at least three metals: nickel, copper, and platinum. Okay, you can see that this curve between R by R naught and temperature. Okay, for platinum it is more or less linear in nature, but if you see for nickel it is nearly non-linear. Okay, but even it is non-linear for shorter temperature range. Say for example, in this temperature range you can consider it to be linear, or even if you see, say for a small temperature range in this region. Okay, this is linear in nature. Okay, so as I have also mentioned earlier, that it depends what is your intended application. So if you are end user, you should know that what is the temperature you expect in your process, and accordingly you can choose based on the cost of these devices. Okay, so if you want your device to be linear in larger range, of course this platinum sensors are helpful, but nickel sensors will be cost effective. But again, you have to see the range of temperature that you intend to use it. Okay, so for short temperature, the linearity is more evident for these devices. This principle is used to derive approximate analytical equations that relate resistance to temperature for a specific metal. Okay, usually this is achieved by linear approximation. So linear approximation is the derivation of an equation for a straight line that approximate resistances versus temperature curve over a certain range. Okay, so it will just approximate your non-linear curve to a linear curve, of course in a certain temperature range. Okay, just have a look for this figure here. Your resistance versus temperature curve is shown. Okay, for different temperature theta 1, theta 2, and theta naught, respective resistances are shown on the y-axis. Okay, therefore what I have done is I have plotted it. I have tried to linearize or find the linear part of this non-linear sensor in this particular range of temperature theta 1 to theta 2. Okay, so in this range it is a straight line representing an approximate relationship between the resistance R and temperature theta. Okay, so a straight line has been drawn between the point of the curve theta 1 and theta 2. Theta naught represent the midpoint of this temperature. Okay, so the equation of this straight line is the linear approximation of the curve from theta 1 to theta 2. Okay, so the equation of the straight line is written as r theta equal to r theta naught into 1 plus alpha theta naught into delta theta, and the condition is theta 1 is smaller than theta 2 and theta naught is the midpoint between theta 1 and theta 2. In this equation, r theta denotes the approximate resistance at theta, r theta naught represents the approximate resistance at theta naught, and delta theta is the difference between two temperature, theta 2 minus theta 1, which is the change in temperature, and alpha theta naught is the resistance temperature coefficient at temperature theta naught. Okay, so the four conductors having the same material with different dimensions, the constant alpha theta naught is basically same. So alpha theta naught is 1 by r theta naught into slope at theta naught, and if you find slope at theta naught for this straight line curve, you will find it as r theta 2 minus r theta 1 divided by theta 2 minus theta 1. Okay, so alpha theta naught is basically 1 by r theta naught into r theta 2 minus r theta 1 divided by theta 2 minus theta 1. Okay, so this is linear approximation. More precise approximation even will be the quadratic approximation. Okay, so a quadratic approximation of the resistance temperature curve is a more accurate representation of the curve over a limited range of temperature. It includes both the linear term as in equation and an additional term that varies as the square of the temperature difference. Okay, so this approximation can be written as r theta equal to r theta naught into 1 plus alpha 1 delta theta plus alpha 2 delta theta square, where alpha 1 is the linear fractional change in the resistance and alpha 2 is the quadratic fractional change in the resistance. Okay, these values of alpha 1 and alpha 2 can be calculated from tables and graphs of the resistance and temperature curves of any particular metal at three different points. So two equations are formed and values of alpha 1 and alpha 2 can be calculated from these two equations. Okay, say consider one example of resistance temperature detector. Say it is built up on platinum. Okay, so for that kind of device, usually for linear approximation gives you r is equal to r naught into 1 plus 36.79 into 10 power minus 40, just for an example. Okay, but if you talk about quadratic approximation equation, it will be even more precise. So that it will give you r is equal to r naught into 1 plus say 39.08 into 10 power minus 40 minus 5.8 into 10 power minus 7t square. Okay, please note that this value 36.79 and 39.08 will be different because in this equation this part has been taken care of. Okay, so this CVD approximation represent this platinum transfer function. Okay, so for the range particularly from minus 200 degrees Celsius to 0 degrees Celsius, the approximation suggests that RT is equal to R naught into 1 plus AT plus BT square plus CT cube into T minus 100, where this T is of course the temperature, and for the range between 0 degrees Celsius to 630 degrees Celsius, it become identical to RT is equal to R naught into 1 plus AT plus BT square. So now this CT cube into T minus 100 term is missing in this. Okay, because of the approximation. Okay, so the constants A, B and C are determined by the properties of platinum used in the construction of these sensors. Okay, there are other approximations also. Say for example, this calendar Van Dusen approximation, another version can be written as RT is equal to R naught into 1 plus alpha into 1 minus delta T by 100 into T by 100 minus 1 minus beta T by 100 into cube into T by 100 minus 1, where T is the temperature in degrees Celsius. Okay, all these approximations will be applicable when you want to detect some temperature at very precision level. Okay, so you increase the precision, this approximation will become more and more complicated because you want to achieve or you want to match this equation with the exact equation that we have discussed initially. R is equal to 1 plus alpha del t plus alpha 2 del t square and so on, alpha n into t power cube, t power n. Okay, so it will try to match that value as close as possible if your approximation is more and more correct. Okay, so the coefficient of this relationship in this equation are A is equal to alpha into 1 plus del by 100, B is minus alpha del into 10 power minus 4, and C is minus alpha beta into 10 power minus 8. The value of delta is obtained by calibration at higher temperature. The value of beta is obtained at the calibration in the negative temperature region. So it will take care, because since you are calibrating, these coefficients are coming from calibration in both the cases where the chance of error is high, be it negative temperature region or be it high temperature region. Okay, the accuracy of these models are very high. Okay, so these RTDs, this approximation in these RTDs, the approximation becomes very crucial. Okay, this is all about RTDs which are based on metals. Okay, in the next class we will discuss another kind of temperature sensor which is thermistors. Thank you.